One of the main applications for all of this stuff about triangles that we've been looking at is finding the distances to things. It seems like that should be pretty straightforward, but the thing is, a lot of distances you would like to measure are actually pretty inaccessible. Maybe you want to measure the distance to something that's in the air or between 2 points where you can't just measure out the straight line distance between the 2 spots. Maybe between the peaks of 2 mountains. You can't exactly walk straight from the top of one mountain to the top of another. But it turns out if you have 2 known spots and you just measure some angles, that's enough enough information to let you figure out all the distances you would like to know. This idea is called triangulation. Spend some time working on the problems on this worksheet. They all generally fall under the heading of triangulation. And if you run into any problems, then fast forward to the point in this video where I work out that problem, and hopefully you can get unstuck. So go ahead and pause the video now. Okay, let's work on number 1. So we have these 2 stations, these 2 tracking stations, I guess, at these 2 spots, A and B. And I guess since they're fixed stations, you can very precisely measure the distance between them because they're on the ground, and so you can take your time and measure this distance precisely. So there's also this airplane going by up above, and the tracking stations can measure the angle up to the airplane. And we would like to know the distance from the airplane to each of these stations. I guess this distance if we follow our naming convention for triangles, we would call this distance B, even though it's the distance from station A. And we would call this right-hand distance A, even though it's the distance to station B. And I guess this top angle we would call C, and the bottom side we would call little c. Okay. And so essentially we just have a triangle solving problem here. We know 2 of the angles already, so we can find the 3rd angle because the sum of angles has to be 180. So C is 180 degrees minus 62.14 degrees minus 33.08 degrees. So that is 180 minus 62.14 minus 33.08, 84.78 degrees. Okay. And now the only things left to find are the sides, A and B. And, we have a side angle pair here. So it seems like the law of sines would be enough to find the remaining, one of the remaining sides. If you tried to use the law of cosines in this situation, you'd end up with both unknown sides in your equation, and so you wouldn't be able to make any progress. So the law of sines is definitely the way to go here. We'd better use the version of the law of sines with the c's in it, because we know both the angle and the side c. And I guess let's start finding the side little a. So we're going to use this version of the law of sines. In fact, while we're at it, why don't we find the side b by using this other version of the law of sines? Okay, so side length c is 2 over sine of 84.78 degrees equals side length A over sine of 62.14 degrees. Okay, and then for the other one, we again get 2 over sine of 84.78 equals b, little b, which we don't know yet, over sine of 62.14 degrees. Let's see, rearranging these to solve for little a and little b, we get little a is sine 62.14 degrees over sine 84.78 degrees times 2. And then for b, we get little b is almost the same thing, but this, I've made a mistake somewhere. This angle shouldn't be the same as that angle. Oh, this shouldn't be 62.14. This should be 33.08. There we go. All right, so little b is sine 33.08 over sine 84.78, all times 2. All right, so now we can just dump all of this mess into a calculator and see what we get. So for A, make sure we're in degree mode. Sine 62.14 divided by sine of 84.78, all times 2. That gives me 1.776 kilometers. This is in kilometers because this 2 was in kilometers, and sines, trig functions produce pure numbers. So this ratio of sines in front is just a number times something in kilometers gives us something in kilometers. Okay, that's for A. And then for the side little b, it's sine of 33.08 degrees divided by sine of 84.78 degrees, all times 2. That's 1.0961 kilometers. Okay, great. Just as a quick sanity check, since the side little b is shorter, the angle big B ought to also be smaller than the angle A, and that's true because the angle B was 33 degrees and the angle A was 62 degrees, so it makes sense that little b is shorter than little a. All right, so pause the video here and try problem 2. Okay, let's have a look at number 2. So this time we have an island, and everybody's supposed to stay 10 nautical miles away from the island. We're in the police boat over here, and there's this other boat. We need to know if they're too close to the island, because if they are, we have to give them a ticket. So we happen to know that we're stationed 5 miles, nautical miles, I guess, from the island. And we can also measure the angle to the island, and I guess somehow maybe we have some sort of radar device that lets us measure the distance to the boat. So what we need to really know is the distance from the boat to the island. That's this side over here. So why don't we name everything? Let's call this side, I don't know, little c, and that angle capital C. We can call the boat, why don't we call that B, and little b is up here. And then this side would be little a, and this angle at the island would be capital A. Okay, so in this whole thing, what we really want to figure out is C. We need to know, is C bigger than 10 or less than 10? So we want to know C. We know this side and this side, so we want or have all of the sides, and we have one angle as well. So that's sort of a case for the law of cosines, actually, right? Because the law of cosines will use all of the sides and the one angle that we know. And so this unknown side will be the only unknown. So that's what we'll do. We'll use the law of cosines. We just need to be careful when we write down the law of cosines that we make the side and the angle be on opposite sides. So that means the side c squared should be on one side, and cosine c will show up on the other side. So c squared is a squared plus b squared minus 2ab times cosine of c. Okay, so there's the version of the law of cosines we're going to use. C we don't know, so we'll leave that as c squared. A, little a is 9.62, and that's squared, plus little b is 5 squared, minus 2 times 9.62 times 5 times cosine of 84.19 degrees. All right, now we can dump all this into a calculator and make sure that you're in degree mode. So 9.62 squared plus 5 squared minus 2 times 9.62 times 5 times cosine of 84.19 degrees. Okay, I get 107.8. And then take square roots to get c. We don't have to worry about the negative possibility for the square root because c is a distance. It has to be positive. So square root of that, I get 10.38. And this is in miles because it's a distance. All right, so that boat is 10.38 miles from the island. And that's bigger than 10 miles. So I guess that means no ticket for the boat. Okay, so pause the video here and try the next problem on your own. Okay, let's have a look at number 3. So one cool thing about triangulation is it turns out that you can triangulate in 3 dimensions just as well as in 2, and you still only need to have 2 observers. So that's sort of interesting. So let's look at this situation. We have 2 observers. They've carefully set up their observing stations so that they're 11.08 miles apart. And they see this falling meteor, and they measure the angles to the meteor and also the angle between the meteor and each other, like this. Okay, and we want to figure out sort of how far up is the meteor, so that would maybe this right here, h, and also how far was the meteor from each observer. So that's going to be these diagonal distances here. All right, so if you look carefully at this situation, there are 3 triangles. There's a vertical right triangle right here between the observer, the meteor, and the spot on the ground that the meteor is over. So that's one of our triangles, and it is a right triangle. There's this second right triangle on the right, and that's the meteor, observer B, and the spot on the ground that the meteor is over. So that's a right triangle. And then there's a triangle lying on the ground that might not be a right triangle. We don't know for sure. That's the triangle between observer A, observer B, and the spot on the ground that the meteor is over. Okay, so if you look at the vertical triangles, for each of them we know 2 angles. We know a right angle and then one of the other 2 angles. So that's going to be enough to figure out these top angles here. So on the one on the left, that's 180 minus 90 minus 17.61. So that's going to be, what, 72.39 degrees? And that's right here. And then this angle right here is going to be 180 degrees minus 23.68 degrees minus 90 degrees. And that's going to be 66.32 degrees. So for the 2 vertical triangles, we know all of the angles, but to find any sides, you have to know at least one side. So on the vertical triangles, we're kind of stuck. So let's try the flat triangle. At the flat triangle, we at least know a side. We do also know the angles, so we can find the remaining angle in this flat triangle. It's 180 minus 37.88 minus 58.03, and I'm going to have to break out a calculator for that one. So 180 minus 37.88 minus 58.03, so 84.09 degrees. Okay, and now we know an angle side pair. So Now we can use the law of sines to find the sides on that bottom triangle. So maybe let's call this one B and this one A. Then we have sine of, A over sine of the opposite angle, so sine 37.88 equals, let's see, the side angle pair that we know, so 11.08 over sine the opposite angle, that was this one, 84.09 degrees. While we're at it, we're going to need the side length B as well, so let's find that one. B over sine opposite angle is 58.03 equals, and then we're going to use the same known side angle pair here, so 11.08 over sine 84.09. Okay, this is, now it's very similar to the first problem on this handout. So A equals, it's going to be sine 37.88 over sine 84.09 degrees, all times 11.08. And then for B, we're going to get sine 84.09 degrees over, sorry, that's not right. It's upside down. Sine 58.03 degrees over sine 84.09 degrees, all times 11.08. So now we can put this all into a calculator. A is, so sine of 37.88 divided by sine 87.09 times 11.08. I get 6.81, and this is miles, I guess. And for B, let's see, sine of 58.03 divided by sine of 84.09, multiplied the whole thing by 11.08, and we get 9.45. I'm rounding a little bit there, 9.45 miles. Okay, so now we know the distance from the meteor to, from the start of the meteor track to each observer. I guess the remaining thing that we wanted was this top height here. So now we know B, that was 9.45 miles, and A, that was 6.81. Okay. And let's see. And we want to find this vertical side H. Well, it looks like we have some options, because this vertical side H, it's a part of two of the triangles in this situation. The right triangle, vertical right triangle on the left, and the vertical right triangle on the right. So we could use either one. I'll use the one on the left, I guess. So we have this small angle down here, 17.61, and the adjacent side, that's 9.45, and the opposite side is what we want. So it looks like we should use tangent. So tangent of the angle, and that was 17.61. So tangent of the angle is the opposite side, which was H, over the adjacent side, which was 9.45. Okay. And then rearrange, we get H equals 9.45 times tangent of 17.61 degrees. And then we can dump this into a calculator. So 9.45 times tangent of 17.61. And that's 2.9 995. So maybe I should round this up to 3 miles. Okay, so that meteor, when it started burning up, was 3 miles off the surface of the Earth.